Good morning, everyone, and welcome back to Fundamentals of Engineering with Farhad, Advanced Topics in Mechanics of Materials. In this example, we delve into an interesting concept in statics, mechanics of materials, and also dynamics, which is moment of inertia. Moment of inertia categorized into two main categories. First one is moment of inertia of an area, and the other one is mass moment of inertia. The first one is very useful in statics and also mechanics of materials, and the latter one is useful in dynamics. So for the first one, if you just consider having like calculation of tau maximum, which is equation for that is VQ over IT. This I stands for moment of an area. And for the dynamic example, just consider having a solid sphere in a 3D space with the radius of r like x, y, z are our axis, and then we want to calculate with the mass of m. Then we want to know what is I m, and that's equal to 2/5 of mass r to the 5. We'll talk about it in detail later. And then let's jump to the first one, moment of inertia of an area. So just consider you have like an area in a 2D space, and then Ix with the distance of the centroid is located at the distance of x and y to the axis, and then I sub x moment of inertia of area based off x-axis is equal to y squared dA. It just says if you keep rotating your sample based off x-axis, you have to go with this distance. And if you want to keep your shape in rotation about y-axis, you have to go by x distance. Then I sub y is equal to x squared dA. That's the mathematics of moment of inertia of an area. A mass moment of inertia, though, just consider you have a solid sphere in a 3D space of x, y, z with the radius of r, then Ixx is equal to Iyy is equal to Izz due to symmetry, and that's equal to 2 over 5 mr to the 5. That's mass moment of inertia for the solid sphere. Let's jump deeper to section properties of a material in terms of a bit of concept with their mass. So if we have an area in xy directions, and we want to know what are those moment of the area, we can have like zero moment of an area, and that's nothing but the integration of the element of dA over the entire area, and that's definitely gives us the area. So zero moment of an area is nothing but the area of that part. We have like first moment of an area, and that's integration of, for example, sy is equal to x dA, and also we call that like qy, and that's useful in transverse shear tau max calculation. We'll talk about it in details later on, and that's V Q over IT. So in this formula, Q stands for first moment of an area, and it just comes from this equation. And then we can have like second moment of an area, which we call it like integration of y squared dA for ix, and that's again this part moment of inertia in or second moment of an area or moment of inertia, which goes to denominator of the same equation. So you can see in calculation of tau max, we are using both first moment of an area and also second moment of an area. So let's jump to some of those example. For example, if we have a circle and we want to know what's the first moment of an area of the top part, so that's like in our circle, in the formula of tau maximum, here we have like calculation of q, and q is nothing but a prime times y bar prime, and a prime is this area of the top part, and then distance or y bar is the centroid of the top part to the centroid of the entire area, and that's for a circle or semicircle is 4r, 4 times radius times 3 pi, if this is our radius. This is our radius. Likewise, our area is half of the circle, and then the centroid of semicircle to the centroid of the entire circle is 4r over 3 pi. And also for first moment of an area, another example for a triangle, that's like again calculation of this top portion yellowish area to the entire triangle. So again, that's a q in the top equation, and q is nothing but a prime, which is this area, times y bar prime. Also, another example for first moment of an area would be rhombus, and in this one again we have like q or first moment of an area here, and we have like the calculation of them. I will provide a list of videos in the description of this video, that you will have access to all these calculation. They are related to transverse shear and also chapter 7, and also pure bending chapter 6 of mechanics of materials. If you are interested to review them, uh, just visit the description of this video. Another a visual example of a calculation of first moment of an area would be a nailing example for a hollowed cantilever beam handling a concentrated load at the free end. So for this case, first of all, if you want to calculate the second moment of an area or moment of inertia, uh, this is like you can consider this shape like the hollow shape first. The Ix, which is 112 base cube height for the big uh, triangle, and then consider just the smaller internal area and just subtract that 112 base prime h prime cubed. Then you will get the moment of inertia or second moment of an area for the entire shape. That's again, I will provide you with the link in description if you want to review a detail of this calculation. And then for if you have like a nailing in this situation and you want to calculate first moment of an area for vertical nailing. You can flip-flop this one, but my bad. You can flip-flop this one, the horizontal one, and rotate it like 90 degrees to have both of them like vertical nails, then separate the top part. So in this case, we can have for vertical nail, we need to calculate first moment of an area of this area. So again, Q of B, which is for this area, is A prime times Y bar prime. A prime is the area of the top one. That's the vertical nailing and first moment area calculation. Likewise, if you want to calculate the horizontal nail, so we need to rotate this nail by 90 degrees and then have like both of them in a horizontal condition because we are going to calculate horizontal nailing. Then you will have this area, and in calculation of your first moment of an area for horizontal nailing, your Q is considering this area, and the distances is centroid of the top part to the centroid of the entire shape. And also another example of a first moment of an area would be considering this part, which is the again horizontal nails, and this is like the vertical one. So if you separate the horizontal nail, you can easily see your A prime for the cross section is this part. And also if you want to consider the vertical nailing and just go with the bottom part, it's up to you. You can go with the top part or bottom part, each of those separated sections, but the top part is like a T section and is like harder to calculate. Is the easier part is just this rectangular cross section to go with, but either of them give you the same answer. And then Q bar Q is equal to A bar times Y bar prime in terms of calculation of first moment of an area. Thank you. We'll solve more problems.